All right, everyone, we're going to go ahead and go through the Module 4 quiz review together and just go problem by problem, go over each explanation as well. So first, in problem 1, you're asked to figure out whether each molecule is polar or nonpolar. Now you're given a couple steps. So the first step is just to figure out whether each bond is polar. Now remember to do this. This is back from Module 3. We just take a look at the periodic table with the electronegativity values and then subtract them. So for C and Cl, we have 2.55 for carbon, and then 3.16 for chlorine. And so if I do that 3.16 minus 2.55, we end up getting a value here of 0.61. So 0.61, again, if we check on the bottom here, we have these ranges. And so since it's between 0.4 and 1.99, that would mean that this is a polar bond. So our correct answer here would be polar. Now, for the CH bond, on this one, the bond, we want to check whether the difference between C and H. So we have 2.55 for carbon, 2.20 for hydrogen. So again, we subtract. So we have 2.50 minus 2.20. So that's 0.30. So because we're at 0.30 here, that means we're in this 0 to 0.39 range. That means that this bond would be nonpolar. All right. Now, the question also asks us to label each bond with the delta plus and delta minus. Remember, that's the partial positive, partial negative. So in every polar bond, we're going to label the more electronegative atom with the partial minus, and then the less electronegative atom with a partial positive. So we're going to do that in all of our bonds here. So we have a partial negative on the chlorine, partial positive on the carbon. Now we don't label anything on the CH bonds because those are not polar, so we don't need to label anything. Now we need to figure out whether each molecule is polar. Now to figure out whether each molecule is polar, it's helpful to draw the dipole arrows. Remember, these show where electrons are moving within an atom. And so we're showing that electrons are moving towards each chlorine in this CCl4 molecule. So since they're moving up, down, left, and right, so they're moving in all directions, it's symmetric. That means this would be nonpolar. If we look at CH3Cl, though, we only have electrons getting moved to the right in this one. So since we only have electrons getting moved to the right, that means that this molecule would be polar. Now, based on that, we can help figure out our intermolecular forces. Now remember, every molecule has dispersion forces. Polar molecules have a dipole-dipole force, and molecules that have an H bonded to an N, O, F, or Cl have hydrogen bonding. So I'm going to go ahead and check here. So in our nonpolar molecule, that means it must only have dispersion forces. And in CH3Cl, since it's polar, that means it also has a dipole-dipole force. Now this molecule doesn't have hydrogen bonding because it doesn't have an H bonded to an N, O, F, or Cl. Now some students might get confused because there is an H and a Cl, but they're not bonded to each other. So because they're not bonded to each other, they don't have that hydrogen bonding intermolecular force. Now on to problem 2, we're just asked to show the strongest intermolecular attraction between our molecules here. So first, let's draw our CH3Cl. So our first step here is just to draw our molecules. So I'm going to draw 2 CH3Cls. And I'm going to draw my second one here. All right, so now I have both of my CH3Cls drawn, and I'm also going to label my partial negatives and partial positives again. So I have a partial negative on each chlorine and a partial positive on the carbon. So then what I want to show is that there's an attraction between a partial negative of one molecule and the partial positive of another. So the way that I show that is with that dashed line there. So this means attraction. Now I can do the same thing for CCl4. Again, I start the same way. I just draw my CCl4 first with all of its dots around. And then I draw my second CCl4. Now, once I have it drawn, this one's a little different because it doesn't have any permanent positives and negatives on it like our other one did. So showing it is a little bit more difficult. So what I need to show is that in my bond, the electrons have moved to create a negative or a positive. So I'm just extending my bonds a little bit here just to make it a little bit easier to show that part. Now remember, a bond just represents two shared electrons. So in here, instead of having my electrons shared evenly right in the middle, maybe like this, I'm going to show that the electrons are off to one side of that bond. So if instead I show that my electrons are way over here, that's going to cause there to be a partial negative on this Cl and a partial positive on this carbon. And then in the other bond, I can show the same thing. I can show how the electrons move. So if they're way on the right side of that bond, we're going to have a partial negative on the C and a partial positive on the Cl. So then, because I have an attraction between positive and negative, I can show that attraction. Now notice that my negative and positive are different in both molecules, and that's fine. In a London dispersion force, all that matters is that you show those electrons and where they move within the bond to cause that negative and positive. All right, on to number 3. Let's go ahead and talk about some of our properties. So on this one, we're asked which one will conduct electricity in water, NaF, CCl4, or CH3Cl, and says explain with a molecular model. Now you're also just provided with a dot diagram for NaF just because we haven't seen that one yet. So the one that will conduct electricity is the one that is ionic. Now remember to check whether things are ionic or covalent. I just need a periodic table, right? If it's on the far right side of the periodic table, it's going to be a nonmetal. On the far left is a metal. So ionic means we have both a metal and a nonmetal. So you have Na over on the far left and then F over on the far right. So because we have both a metal and a nonmetal, that means this is ionic. So because that one is ionic, we are able to be sure that that one is our one that will conduct electricity. Now, as to why, we can either draw our own, or we can also just look at some images from our notes to get an idea of what we can draw. So since we've already used that before, let's use that as an example when we come up with our drawing here. So let me pull up that image here. Let's take a look at what we've drawn in the past for ionics conducting electricity and use that as a model. Now here's the section in the notes that matters. So what we're showing here is that when we dissolve an ionic compound, we get positive and negative ions that can flow and move. So they can move towards a positive or negative electrode. So remember, electricity is just flow of charge. So we could draw something similar to this. We could also draw something like this, right? We can show that those negative and positive ions are able to move and flow. So in our drawing here, we can just draw that we have some container, and in this container, it is full of liquid, and we have some Na plus ions, some F minus ions, and these are just randomly distributed throughout our container. All right. Now, because these are free floating and free to move around, we know that these will then be able to flow towards our positive or negative side. So that's an explanation of our model. Now, if I was going to get a little bit more detailed here, I'd also want to add in some of these like positive and negatives, that the negatives are flowing towards the positives are flowing towards the negative. That would just add a little bit more detail to my diagram. All right, now on to number 4, which one will dissolve in water? So remember, to dissolve in water, it has to be able to make attractions to water. Now, since water has a positive and a negative, we then need molecules that also have positives and negatives. So the ones that always have a positive and negative would be NaF and CH3Cl. So NaF is ionic. It has a positive and a negative. So if I was to draw out what it looks like when NaF dissolves, again, I first just draw my container. It has some amount of water in it. And then I can show that around each of the Na pluses, I have water where the oxygen is facing towards the ion because that's the negative side of water. So the negative side of the water will face towards the sodium ion. Now around the negative ion, I'm going to get the positive side of water. Now remember, you can also just draw a water molecule as like a little Mickey Mouse head because we have the one single oxygen and the 2 hydrogens. So that's what we can show here. Now for the CH3Cl, it's slightly different because this one's not ionic, it's just a polar molecule. Now it starts the same, we have our container full of water, and I can draw my C with its 3 H's and a Cl. Now remember, the negative part of this molecule is the chlorine, the positive is the carbon, So when I draw it, again, I'm going to draw it so that my negative of water is facing the positive of water is facing the negative. So I put the two hydrogens of water facing my chlorine, and the negative of water facing the carbon. So this would be a drawing showing why those dissolve. Now, to explain melting point here, we first have to think about what's holding each thing together and preventing it from melting. So for our covalent compounds, those are just held together by intermolecular forces. Now remember, we already identified those up above. We said that the strongest force in CCl4 was a dispersion. And we said that the strongest force in CH3Cl was a dipole-dipole. And then in an ionic compound, the force holding it together is the ionic bond. So that's what we would need to break in order to melt that substance. So in CCl4, we just have a temporary partial charge holding it together. In CH3Cl, we have a dipole-dipole force holding it together, so a permanent partial charge. And then in an ionic bond, we have a permanent full charge holding it together. So that means that the highest melting point would be NaF, and then CH3Cl would be a little bit lower, and then the lowest melting point would be CCl4 because it has that weakest intermolecular force. So my explanation just comes down to the intermolecular forces, right? We have the strongest force in the ionic bond because we have the full positive attracting to a full negative. The CH3Cl is a little bit weaker because it only has a partial positive and a partial negative attracting. And then CCl4 is the weakest because it has a temporary partial positive and partial negative attracting to each other. All right, on to the back page. So this back page is about polymers and metals. So first it asks, polyethylene is a thermoplastic. Now, when polyethylene is cross-linked, it turns into PEX. So it's asking how and why do the properties change? So what we're shown here is, in this first section up here, we have all of the representations of the polyethylene. And then down here, we have the cross-linked polyethylene. Now, what we're changing here is that we are connecting different chains. So because we connect one chain to another, that allows us to have a stronger attraction between chains. So because we have that stronger attraction between chains, it's going to make it so that it's more rigid, and it's also going to make it into a thermoset, because we aren't going to be able to melt and break those attractions between chains like we were when it was just a linear polymer. As a linear polymer, it's just held together by intermolecular forces between chains. So once we make it a cross-linked polymer, we now have covalent bonds. So it's harder to break those, so it's not going to be able to melt anymore. So the main properties that we're going to change, it's now going to be a thermoset, it's going to be more rigid, and it's going to be stronger overall. This is similar to what y'all did during the polymers lab when you took the PVA, which was just a linear polymer, and then added the sodium borate to make crosslinks, and then you had a crosslink polymer that turned it into like the bouncy ball. It had a stronger, more rigid structure, and it would have been a thermoset. Now on to number 7. So number 7, it says iron and steel are both used widely in the metals industry. Now on the left here, this is our iron, and on the right we have our steel. Now it asks which one would conduct electricity better. Now what we've learned is that pure metals conduct electricity more. So the iron conducts electricity more, and the reason is it doesn't have any dislocations or point defects. Now remember, point defects are areas in which the metal crystal lattice has like an error, right? So we either substitute in a different atom, we have one interstitial, or we have one that's replaced, something like that. And that can cause a point defect. Now for a point defect, let me go back to our notes here to show you an image of what that looks like. This is an example of a point defect. So where we have this nice arranged crystal lattice, we have like a nice neat row, and then that nice neat row kind of gets broken. So just like when you are trying to drive down the highway and you go from 5 lanes of traffic down to 4, you get some traffic. That's because we have less lanes to drive in with all those cars. So the same happens in a metal. If we have a point defect, a dislocation that changes the number of lanes, that changes the number of columns that we can travel down here, like this, now that means that we have more traffic. There's going to be less conduction or areas for those electrons to flow. So in the alloy, we then have a lower conductivity. Now the explanation, we could write out that full thing, but it's also just easy to use that picture. You would want to have that on your test or on your review here. Now on for number 7b, which metal would be stronger and why? So again, this goes back to our properties. When you have an alloy, specifically an interstitial alloy, that typically makes the metal stronger. So in this case, the alloy would be stronger. So the steel is our answer. Now, as to why that is, again, we can go back here. So dislocations cause a metal to be less malleable. Now, the reason is, if we look at an interstitial alloy here, we can look at something like this with this defect here. When we have this atom in the center here with that defect, it can prevent two planes of atoms from sliding across each other. So if we can't slide across each other, it's going to make that metal more rigid and less likely to bend and be malleable. So when we have more dislocations or more point defects, that's going to cause there to be a higher strength to that metal, and it's going to be less malleable. So in this case, the steel has all of these interstitial atoms, right? Every single one of these carbons up here is an interstitial atom, so that means it's going to be a lot harder for this metal to bend and be malleable because of all of those point defects causing dislocations. All right, so that is the end of our review, and that's where we are going to stop. If you have questions, try and look through your notes to find some answers. Good luck reviewing, and good luck on your quiz tomorrow.